So how do we go about finding these corrections, right? So we know the zero order and we want to find the corrections. So we make some assumptions. First, we assume that our total Hamiltonian, including both our unperturbed and perturbation, acting on our zero order wave function, is approximately equal to the total energy, including the correction, times our zero order wave function. So we can show that so using an expectation value, so we can find what's our expected average energy. So we can say the average energy is going to be, and this is approximate, this is not equal, but is approximately equal to the integral of psi 0 star times h total psi 0 d tau. All right, and so this is over all space. So we can go ahead and substitute what we have defined E total to be. So the energy is approximately equal to psi 0, let me write that clear, star h0 plus h1 times psi 0 d tau. And so that'll give us two terms. So we'll have our first term, the energy is equal to the integral of psi 0 star h0 psi 0 d tau. And then a second term that involves the perturbation, psi 0 star h1 psi 0 d tau. Now let's take a look at this first term. Well, the first term we have our unperturbed Hamiltonian acting on our unperturbed wave function, and that will just give our unperturbed energy. And so we'll get the E0 times psi 0, and this is just a constant that we can pull out of the integral, so we'll end up with E0 times the integral of psi 0 star psi 0 d tau. And assuming these wave functions are normalized, this will just be equal to 1. Right, so this is just the normalization integral. Okay, and then so that's our E0 value, and E1 will just be what's left. So E1 is this integral right here. Okay, so the final result, what we need to know, is that the first order energy correction is equal to this integral of our zero order wave function, basically the expectation value of that with the perturbation. All right, in the next video we'll look at the corrections to the wave function.